Hello and welcome to this webinar in which we'll discuss how to take on the challenge of complex data modeling with machine learning. And more specifically, we'll see how and why we could want to go further than the classical multivariate linear models like PLS. I'm Astrid Maléchaux. I'm a data scientist at Ondalis, which is a company that was created in 2003. We are based in the south of France near Montpellier, and we now employ a multidisciplinary team of 8 people. Our core business is research and development of chemometrics and machine learning models with applications in different sectors. And we also do consulting and training. But for this webinar, I will focus on machine learning models for complex data. And we'll see first what can we call a complex data. So first of all, there is a complexity related to the nonlinear nature of relationship that can exist between the predictive variables that we will call X and the response that we want to predict and which we will call Y. And so, for instance, here in the regression case, we could have, of course, a linear relationship as in this first picture, but it can happen that we have a non-linear relationship between the variable X and the response Y. And in this case, a linear model like PLS will not be enough to correctly model this relationship. In the case of classification also, we could have, sometimes we can have a linear separation between classes or groups, but it can happen that the separation which would be required here in the last picture is nonlinear. And so again, a linear model in this case would not be able to correctly discriminate these two groups. A second type of complexity would be when we have a database with many sources of variability in our samples. For instance, we could have very heterogeneous data or even a clustered database. And this could be caused by several effects. First of all, we could have heterogeneity related to the samples. So if we have, in this first figure here, we have a PCA showing a year effect. So same samples, same kind of samples, but the spectra were acquired over different years. So it could be different vintages. We could also have different varieties, for instance, in agri-food samples. Different particle sizes also could influence the spectra, or in chemistry, you could have different production grades, which would cause clusters in our database. We could also have an effect, a variability related to the instruments. If we want to predict the same parameters, but with spectra acquired with a network of different spectrometers, so they could cause, again, some variability in our database. And finally, we could have variations related to measurement conditions. For instance, here in the last picture, we have a PCA showing a location effect of samples measured in the field. So yeah, different conditions, variations of temperature. It could also be like in a factory if different operators are measuring the spectra, etc., etc. And finally, a third kind of complexity would be if the parameter is complex to predict because the variation of the parameters that we want to predict are not directly related with the chemical information contained in the spectra. And in this case, for instance, we could have, if we want to predict a physical parameter like texture, rheological characteristic, or particle size or things like that, or another kind of complexity, like if it's sensory characteristics, or varietal or geographical origin of the samples, durability of the samples, and so on. But keep in mind, however, that this sentence like garbage in, garbage out, like if the information that you want to predict is really not measurable, not present in the sample. You can try more advanced machine learning models, but if the parameter is really not measurable with the technology that you're using, or if you're trying to predict concentrations that are below the detection limit of your instrument, it will not work anyway. And also, unfortunately, if your reference measurement that is giving you the known values to train your model, known values of the response that you are trying to predict, if the reference measurement is too noisy, unfortunately, you will not reach good performance with your model, even with a more advanced machine learning model. So with that being said, we will see different kinds of machine learning methods that can help us to tackle this complexity in our data. So for this webinar, we will focus mostly on supervised learning, but you see here that there exists also another family that is unsupervised learning, based only on the predictive variables, so for instance, the spectra, and that is trying to find the internal representation of these spectra. For instance, there are groups based only on the spectra. But for this webinar, we'll focus on supervised learning, where the model is given to train on the one hand, the predictive variables, so for instance, the spectra, and on the other hand, known values of response. And so the model can train. And if the response is a class or a group, it will be a classification model. If the response, on the other hand, is a quantitative value, it will be a regression model. For this webinar, we'll focus again on supervised regression models mostly. And we will see so locally weighted regression. Then we will see support vector machines. Then we will see ensemble methods based on regression trees. And we will see two ensemble methods, random forest and extreme gradient boosting. And finally, we'll talk about artificial neural networks.